Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the transformation technique for a continuous case. So here the technique is used to find the PDF of a new random variable. And here are the simple steps that you have to remember. The first step here is, let's say you have a function, a new random variable y, that depends on this function here. We call it u, and this function here has x in it. Okay, now you need to convert and let x be the subject. So here you will be able, or you should be able, to express x as something related to y, and here we call the function of y as w. So w here is a function that contains y in it, and you're going to differentiate wy. Okay, so that's what you're going to do. You're going to differentiate wy, and once you're done with that, you're going to apply the formula given here in order to find the PDF for y. So this is the PDF of our random variable, and you are going to substitute wy into this function f. So what is this function? Function f here is the PDF of the original random variable, which is x here. Okay, so you're going to substitute the result here because this is x is equal to wy. So basically you're going to substitute wy into this place of x, and f here is the function, is the PDF of the original random variable x, and the result here is going to be multiplied with the absolute value of the result you get on the second step. You differentiate this function with respect to y, and you find the absolute value of it. Okay, so this second step here is going to be applied here. The first step here is going to be applied right here in this formula. And I believe that the process here can be better understood if you look at the example, and that's what we're going to do next. Okay, so in this example here, we have a random variable x that has the exponential distribution that looks like this. Here x is greater than 0, and we have a new random variable y, which is equal to square root of x. So here is the function which is defined as ux, as given by this part here. So y is equal to something, a function that has x in it. Now, in order to solve this, we are going to start with the first step, which is to change y and let x be the subject. Okay, so here we have y is equal to square root of x, and this is the same thing as saying that x 1 over 2 is equal to y. And how do we get rid of this exponent here, 1 over 2? In order to get rid of that, I have to introduce 2 outside, and of course on the right hand side also we have to do the same process. And by doing that, you can cancel out 2 here with the one at the bottom, so you are left with x is equal to y squared. So that is the first step. And this is what we call wy. Okay, so this is wy. This is a function that has y in it. So w here is a function, and we are going to substitute this big y as small y, and we're going to just plug into here, into this PDF. So what is f in this case? Well, sorry, oops. So what is f in this case? It will be this one right here. So here is fx, where you are going to later on substitute the result here into this function. Okay. Now let's look at the second step. The second step is we got to differentiate what we have right here. So I'm going to change this to using the small notation of y, wy, because the small y is applied here, right? Well, so here wy is equal to y squared, and if I differentiate that with respect to y, that means I'm going to differentiate y squared, really, and the answer is going to be equal to 2y. Okay, so here is w prime y, this is wy, and next we are going to just apply the formula. Okay, so maybe we can use the next page. Next we're going to apply the formula. Step 3 is apply the formula. So here we have fy is equal to, we're going to take the function of x, which is this one, and you're going to substitute wy into it, into the position of x. You're going to multiply that with the result of the second step, which is derivative of the function, and you need to find the absolute value of it. So what is wy? Well, this is y squared. You're going to substitute right in the x position. So here we have equals to e negative, and here we have y squared times with the result of the derivative is 2y, so we need to find what's the absolute value of 2y. The absolute value of 2y is 2y, so just write down the result and we are done. Okay, and we need to know what are the values that y can take. Okay, so here is the PDF of random variable y, and y can take what value. So in order to know what values y can take, we have to refer to this part here, the values that x can take. X can take, from that you can see that x can take values that is greater than 0. The values that x can take. So x is greater than 0. What is x? X is this guy equals to y squared, which we can replace at this position. Therefore, we can say that x is equal to y squared. It's greater than 0. And this can be further simplified. You can say that if I introduce 1 over 2 on this left hand side, and again 1 over 2, this one here can be simplified as y, because this can be cancelled out. 2 and 2 greater than 0 to the power of 1 over 2 is still 0. So now I can write down that for this PDF here, this one here is for y greater than 0 as well. So this is the final answer. Okay, right, now let's move on to this part here, where we can extend the technique that you have seen to a case of two continuous random variables. So again, when you have two random variables together, then you will be interested to find the joint PDF. Okay, so this will be your interest, and here is the explanation regarding finding the joint PDF. Okay, right, okay, here we have the two random variables x1 and x2. This is the information that we have. We have x1 and x2 as the original random variables, and together they have the joint density function, which is described by this f x1 x2. Yeah, and then imagine that we have another two random variables. We have y1 and y2, and y1 here is equal to something, a function. So here is a function that has x1 and x2 together. So here is a function that has x1 and x2 together. We call this function u1. Okay, next y2 has is equal to some function here that has x1 and x2 as well. So this is y2. Therefore, what we have to do is, in the first step, we need to let x1 and x2 be the subjects. And you can see that this process here is similar to what we have done before in the case of one random variable. Okay, so the first step is to make sure that x1 and x2 be the subjects. Therefore, by doing that, we are able to find this one here, which is a function of just y1 and y2, and there's another one defined as the second function that has y1 and y2 as well. So here we have w1 is a function, w2 is also a function. Next, what we have to do is, on the second step, we have to differentiate the result that we got here. So we're going to differentiate these two functions here, and basically we are doing the partial derivative. So here are the partial derivative, and the whole process here of finding the partial derivative and finding the determinant of this 2 by 2 matrix is called J. So J here represents or how do I say this? J here is the Jacobian process. I think I'm just going to call it Jacobian. Okay, so here J here is Jacobian. Some people call this Jacobian determinant. Well, I'm just going to call it Jacobian then, as simple as that. So what it does really is you need to differentiate this with respect to first y1, and then you have to differentiate this same function with respect to y2. Okay, similarly, you have to take this function, differentiate it with respect to y1, and then you do it with respect to y2, and you have to find the determinant of it. And remember, if you have a 2 by 2 matrix where you have A, B, C, and D, if you want to find the determinant of it, this is just equal to cross multiplying the result here. We have A, D, and then minus the result of B and C multiplied with B, C. So that's a process that you will see going to be applied in this part here. Okay, so that's the second step related to finding the partial derivatives, and it is similar to the case of one single random variable. You differentiate something on the second stage. Yeah, now on the last stage, we're just going to apply the formula that looks like this. So basically what you have to apply is you're going to supply the result here at this position. This is the result, and the result here at this position. Of course, you got to change this one to a small random, to a small value. So here is random variable, but this one is, we're going to use specific value representing y1, y2. So we have small alphabets for that one, yeah. And basically this is the position for x1, and this is the position for x2. So here you are going to substitute the result here that you have on the first stage into this original function, original joint density function of x1 and x2. And the result here is going to be multiplied with the absolute value of the process in the second step. So the second step here has some result. You're going to supply the result here and find the absolute value of it. Okay, so again, what I'm trying to say to you is that the process here is very much similar to what you have seen in the case of one single random variable. Okay, now without further ado, we are going to look at the example here. Suppose that, well, we have two random variables, x1 and x2. They are independent exponential random variables, both with the same parameter, lambda is equal to 1. Therefore, we are looking to find the PDF for each x1 and x2. Now, before we can do that, we need to recall some facts related to exponential random variables. So if you have exponential random variable. Therefore, your PDF is going to look like this. Okay, so this is what you have seen before in chapter 6, I think. Yeah, previous chapter. So now lambda is equal to 1. Therefore, the PDF here is going to be reduced to e negative x. Okay, lambda is equal to 1. Therefore, you get e negative x. Now, if you want to write down the PDF for each x1 and x2, it's going to be just applying this function here and replace x with x1 and x2. Okay, so here is the exponential, the PDF for a random variable x, where x is exponential random variables. Therefore, for question A, the PDF for x1 is going to be x1 e negative x1. Since x1 here is exponential random variables with parameter lambda equals to 1, yeah? And we're going to write down for x1 greater than 0. Next, for x2, we have PDF for x2 is going to be the same thing because it is exponential random variables. So here we have e negative x2 for x2 greater than 0. So we are done for the first part. Now let's move on to the second part, which is to find the joint probability density function for x1 and x2. Now fx1, x2 here can be simply written as x1, the PDF of x1, multiplied with the PDF for x2. Why is that so? Because it says here that x1 and x2 are independent. When they are independent, the joint PDF can be simply obtained by multiplying the first PDF and the second PDF. Okay, so here we've got e negative x1 times with e negative x2, and we can combine that to be e negative x1 minus x2 for x1 greater than 0 and x2 greater than 0. Now the next part is we are going to find what is the joint PDF for the new random variables. We have y1 and y2, where y1 is defined by this guy and y2 is defined by this one. Okay, so in other words, this is the notation given by this one here. We have u1, so this is u1 that depends on x1 and x2. U is a function, and this is u2 that also depends on x1 and x2. So here we have x1 minus x2, x1 plus x2. In order to find the joint PDF of it, the first step is we are going to try and express x as a subject. Okay, so here what we have is this one, x1 minus x2, x1 plus x2. So we're going to make sure that x1 and x2 be the subjects. We have to write down x1 in terms of y1 and y2 and x2 in terms of y1 and y2 as well. Okay, let's try and do that now. Well, here we have the information given, which is y1 is equal to x1 minus x2 and y2 is equal to x1 plus x2. Therefore, from this part here, I can write down x1 is equal to y1 plus x2. I'm referring to just this part. I can rewrite that as x1 is equal to y1 plus x2. Yes, I'm going to call this equation 1. And if I look at this part here, I can write down x1 is equal to y2 minus x2, and I'm going to call this 2. Maybe I should write down equation 2 right here at the bottom of equation 1. So here we have x1 is equal to y2 minus x2, and this is equation 2. Okay, now what I'm going to do next is I'm going to subtract. Okay, I'm going to have equation 1 minus equation 2. So 1 minus 2. So if 1 minus 2, x1 minus x1 at the bottom, the result is going to be 0. y1 minus y2, so that is the result, y1 minus y2. x2 minus x2, so x2 minus negative x2 is 2x2. Yeah, so that's the result. And based on this, I can express what is x2. Therefore, 2x2 is equal to y2 minus y1, and x2 is just y2 minus y1 over 2. So what I have here is x2 in terms of y1 and y2. So I'm going to call this function as w2 y1, sorry, this is y2, w2 y1 y2. So here is the part where I have managed to express x2 in terms of a function w, and w here has y1 and y2. Okay, next what I can do is I can use the result here, and I can substitute into this part. Okay, so from 2 we have x1 is equal to y2 minus x2. Okay, so next what I can do is I can substitute x2 into this part. So here we have y2 minus y1 over 2, and that becomes you can simplify that to be 2y2 minus y2 plus y1 over 2, and that becomes y2 plus y1 over 2. Okay, so here is y2 plus y1 over 2, and this part here is w1 because you are going to talk about x1 here, so we call it w1 that has random variables y1 and y2. So this is a function that has these two random variables. So that's the first step done, and what we're going to do is we need to go to the second step, which involves finding the partial derivative and the determinant of that. Okay, well, maybe what I can do is I can write down the result at the top because I need the space. So here, let me just write down. We have w1 in terms of small alphabets because this is what we need to do later. w1 y1 y2 is y2 plus y1 over 2, and then w2 y1 y2 is y2 minus y1 over 2. So this is the result that we have managed to obtain, and well, I'm going to erase this part. Okay, hang on. Okay, next is we're going to focus on the second step. So here is the second step, which is related to finding the partial derivatives and then get the determinant of it. So here we have Jacobian defined as, what you need to do is you need to differentiate, uh, actually partially differentiate this function. So here we have y1, and here is the function w1, y1, y2. Okay, and then we're going to do the same function, going to look at the same function, but we're going to find it with respect, we're going to differentiate it with respect to y2. Okay, so this is for the first part, this one. And then we're going to consider the second part, which is this one here, the second function. Differentiate it with respect to y1 first, sorry, w2, and then take the same function and differentiate it with respect to y2. Okay, so that's the process that we're going to do now. Well, if you differentiate this with respect to y1, I hope you can see that the result is going to be just 1 over 2, right? 1 over 2. And then if you differentiate this function, oops, God, what's going on? Oh, hang on. Okay. Okay, so next for this one, if you differentiate this with respect to y2, the result is also going to be 1 over 2. Now, next, differentiate this with respect to y1, the result is negative 1 over 2. Differentiate this with respect to y2, the result is going to be 1 over 2. Okay. And we're just going to continue the process. We're going to find what's the determinant of it. Okay. Therefore, we're going to multiply 1 over 2 with 1 over 2, cross multiply 1 over 2 times with 1 over 2, minus, cross these two values and multiply them. So I have 1 over 2, negative 1 over 2. So here we have 1 over 4, sorry, here we have 1 over 4 plus 1 over 4, which is going to be 2 over 4. This is just 1 over 2. Okay, so that's the result on the second step. Okay, maybe I will write down the result right here. Okay, so here is 1 over 2, yes, because I need the space. I'm just going to erase all this. Okay, now next is we're going to apply the third step, which is applying the formula. So here is the third step in order to find the joint probability density of y1 and y2. We need to substitute this guy here. So here we have w1, y1, y2, and then here we have w2, y1, y2, and you're going to multiply that with the absolute value of this Jacobian result that we have here. Okay, so now what is f? So f is given by this part. This is f, and we're going to substitute this guy at the position of x1 and this guy at the position of x2. So here we have negative x1 and negative x2, okay? All right, so that becomes e negative, well, y2 plus y1 over 2 minus y2 minus y1 over 2. So that's the result, multiplied with Jacobian result is 1 over 2. Okay, this is the absolute value of 1 over 2, which is going to be 1 over 2 as well. Well, here we have 1 over 2. And we're going to simplify this top part here, and it's going to be 2 negative y2 negative y1 negative y2 plus y1. So that is how we can start thinking about it. And then we can see that positive y1 can be cancelled out with negative y1, and then you will have e negative y2 is negative 2y2 over 2, which can be cancelled out as well. So final result is 1 over 2 e negative y2. Okay, so that is the final result. And this one here is going to be 4. We know that here this one is for x1 greater than 0 and x2 greater than 0. Therefore, for this one here, we're going to have for y2 plus y1 over 2 greater than 0 and y2 minus y1 over 2 greater than 0. So that's the answer. This is the joint PDF for two random variables y1 and y2. Okay, that's all for now. Thank you very much for watching.